a cool theorem for you. Suppose you have two subspaces and you want to show that the intersection is also a subspace. So here you have, for example, a vector space like U, and then here you have two subspaces like V and W. And you want to show that their intersection is also a subspace. So even if you shrink it in the size, you get another subspace as well. So this is not W. Okay, here we go. I'm sure that this guy is also a subspace. Perfect. So let us start the proof. We need to show that this intersection is non-empty. This is our very first step. Since V and W are both subspace of U, then they both include the zero vector. So zero vector belongs to the intersection. So for now, we're done with the intersection being non-empty. Now we need to show that it's closed under addition. Now we show that the intersection is closed under addition. So what are we going to do? We're going to take two vectors from the intersection. So we need to show that if, for example, V1 and V2 are both in the intersection, then their addition, V1 plus V2, is also in the intersection as well. So I'm going to put a question mark here because we're trying to show this. All right. Very good. We're going back to the properties of intersection that you learned in elementary algebra. Since V1 belongs to V intersection W, we conclude that V1 belongs to V and V1 belongs to W. Again, since V2 belongs to the intersection, it means that V2 belongs to V and V2 belongs to W. Very good. Since V is a subspace, so it is closed under addition. It means that V1 plus V2 belongs to V. The same argument for W. Since W is a subspace of U, so it is closed under addition. So V1 plus V2 also is in W. So basically you can conclude that V1 plus V2 belongs to their intersection. Okay, perfect. We're done. Scalar multiplication is also easy as well. So we show that, now show that the intersection is closed under scalar multiplication. So as usual, let, for example, vector V belongs to the intersection and C belongs to a field. You can take this field to the real field or any field as well. We show that V is also in the intersection. Put a question mark. Okay, perfect. As usual, since V belongs to the intersection, so V belongs to the first subspace and V belongs to the second subspace, but both V and W are closed under scalar multiplication. So CV belongs to V and CV belongs to W. So you can conclude that CV belongs to the intersection. So we showed that the intersection is non-empty. It's closed under addition and it's closed under scalar multiplication. So what is our conclusion? The intersection is also a subspace.